Hi everyone. Today I will no. Can you hear me?
Yes.
Yeah. I will introduce you how to use MRSF. Just a basic implementation with the ROHF wave function. Today I will introduce 5 calculations in this order. In games, let's have a look at the optimization calculation first, the info file. In games, there are many kind of groups, which is separated by this dollar group and $end. So here I show something important in black and which is not important in gray. So let's have a look one by one. This SCF TYP type is a wave function type. So here MRSF uses ROHF as a reference wave function, so we use ROHF. And the multiplicity of ROHF orbital is a triplet, so we use 3. And just simply give a run type as a optimize. And I charge is charge of molecule. And MRSF use spin flip TDDFT, so just give spin flip and give DFT functional and the maximum iteration of SCF cycle here. And then in this TDDFT group, this N state means the total number of states to be calculated. So for example, if it's 3, it means one ground state and 2 lowest excited state. And I root is the target state to be optimized. In MRSF, 1 index means the ground state, and 2 is first excited state, and so on. And here we have to choose whether we want to calculate singlet or triplet. So for singlet, we use MRSF S for singlet and triplet for MRSF T as a true. So you can choose one of these two options. And
you can choose both, right, at the same time.
I've never tried actually. Maybe it's possible.
Okay.
I don't actually know. So for singlet, you give 1 as a multiplicity. And for SCF group.
So sorry about the interruption.
Yep.
So this is a quite confusing input. As you can see that in the control group, you have a multiplicity is 3.
Mm-hmm.
And then yes. TDDFT, you have a multiplicity is 1.
Mm-hmm. Mm-hmm.
So this is quite confusing because the same looks like a multiplicity. One times 3 and the other 1. So it's confusing. So this is one of the interesting part of the game's input. So in the control, the multi is for the RHF reference. Okay, so the multi 3 is for the reference wave function. And then the multi 1 is the one that target states or the response states. Mm-hmm. So I guess in this case, he said MRSF equals S is true, means that you are going to calculate singlet. So the multiplicity is 1, right? Yep. However, what about the MRSF equals T, which is a triplet? Mm-hmm. Woojin, can you tell me what the multiplicity is for that triplet case?
Yeah, then you should choose 3 for this multiplicity.
Is that right? That's the question. Because of even triplet, we calculate M sub S equals 0. But that's M sub S equals 0, right? So, but the multiplicity wise, a triplet, right? So there's some confusion between M sub S and the multiplicity itself. So multiplicity-wise, still in the case of triplet, it's a 3. It has to be 3 if you want to calculate the triplet response states, right? So, but I can tell you more about that, but it's a bit confusing later because then the actual triplet we are calculating is M sub S equals 0. So, but M sub S is just a microstate of a triplet. So, so in terms of a multiplicity, still triplet has to be 3. So it's too confusing, right? Sorry, sorry about that.
Yeah,
so,
and
yeah.
And also, so firstly, for reference state, we always use multiplicity 3 because reference state is always triplet. Yes.
Sure.
Yes.
For here, at the present implementation, the two multiplicity MRSF, CFS, it is they are tightly they are, how to say. Actually, one is unnecessary, yes, in principle, yes. So if you use singlet, it must be 1. If you use triplet, it must be 3.
Oh, very sharp,
and so,
sharp.
and
Yes.
you don't, in principle, you don't need the other keyword, and
Exactly.
it is kept,
Exactly.
it is kept for some future modifications, yes.
Exactly. That's exactly. You're right, and very sharp observation. So. If it's MRSF, you don't need, it's of course, multiplicity is 1, so you don't need it. So if it's triplet, the multiplicity has to be 3, so that you also don't need it. But so why we need to specify multiplicity here? That's the question, right? So so that's a part of life, I would say.
No, I just thought maybe some for future changes, it's just for convenience. Yeah, okay, fine.
Yeah, Woojin, you understand her point, right? If
yes,
it's I mean, multiplicity in the TD-DFT part simply don't necessary, right? But then that's what we do. Yeah.
Sorry, at the same time, TD-DFT can calculate only singlet if this approximation. No. Is it possible to calculate triplet? No?
Exactly, exactly.
Yeah, sure.
Okay.
So
then you should give MRSF T as a true for triplet.
The keyword is so it's a T at the end, not S.
Yes, yes, this one.
So then it's a triplet, yeah.
And one more question.
You have okay.
What this is unimportant. TAMD equal true. What does it mean? Sorry.
It's Tamdam approximations.
That's a very good observation again. So
what?
Okay, so it's they call it Tam Dankov. Tam Dankov is a person. Okay, so there's a people name, Tam Dankov approximation, or in some other literature, TDA. That's what if you read a paper, TDA is the Tam Dankov approximation, and here keyword is TAMD. So kind of it's supposed to be TDA, but that's what they did originally, so we couldn't change it. So what it does is that in the case of TD-DFT, you need to form 2 different matrices, consider A and B matrix. Okay, so it's very simple, A and B. Okay, what the Tam-Dankov approximation does is that you skip B, you only calculate A. Oh, very good, right? So you reduce a lot of computer time, and it's a pretty good approximation, in fact. So Tam-Dankov simply means that we only calculate A matrix, not B.
I see, and this is an input file not for the implemented but for local. Which keywords is for local implementation of GACE? Which one for commonly used for official version?
I guess the main difference, the lowercase one, the MRSFS.
This one. Okay, it is this. It is the only.
That's the only one.
Yes.
Okay, thank you.
And Professor Blood, you
maybe MRSFS equal true. At the same time means control multiplicity equals 3. Both keyword means the same. MRSFS means multiplicity 3 in control. That's double call. Yes, was the same. For example, if I put multiplicity 3 in control and change MRSFS into DFT to not true, no, yes, it will not work. Just you in program somehow it's not finished.
If you said no, it will calculate spin flip, not the MR spin flip.
MRC anyway use multiplicity 3 in control, just because anyway.
In the control, yeah. Control always has to be 3, yes.
Yeah, if you use ROHF.
Okay.
Even if you use a UHF, that's what we developed recently. That's also multiplicity is a 3. So I think that's why we need a new program, okay? That is much easier. So just have one keyword that will do all the rest. You don't need many of this. But this is the way the games is working. So each group read it separately, independently. That's why we need to give it this. So we are going to make a new one, which makes it much easier.
Okay, and for SCF group, it's just simple. This is a flag to the direct SCF calculation. If you turned off, this is very slow. So, and after turning on this, you can choose one of two optimizer, SCF optimizer. You can choose one of these two, and the rest.
You have to explain the couple. So the second line, that's a very important. It's a gigantic keywords. Please just copy and paste every time you do it, okay? So don't think about what it is. But I can explain it to you, but we can tell you. The reason we have this is that the ROHF implementation, you have a multiple choice of ROHF. There is no unique ROHF. And Saunders is the one that simplest thing. And the real problem is that during DFT calculation, you use RHF, particular RHF. And then TD-DFT part, you also need to use RHF. But what we found is that default setting is different. They use both the same RHF, but then for the DFT, they use a different, he likes, I think Mike, not Michael, okay, there's another Mike Schmidt. Mike Schmidt likes one of his friends, so he just put it as a default. But for the TD-DFT, they use a different RHF choice. I found that's one of the major reasons why the convergence has a problem. So the only way to get it the same way is this. Just copy this, which makes even the SCF part, the DFT part uses identical RHF wave functions. So that's, sorry about this. This is, I didn't do it. Okay.
Okay, here, and I use 6-Ryonji star. And the maximum iteration of optimization calculation, and the time limit and the memory.
Why so strange number of time limit? 9999.
Yeah, it's just if you give small time limit before calculation finished, it died. I mean,
yeah, I know what means time limit. Just if you remove it, what's happened?
This number is the original file I gave to the students, and then students use the same number.
Yeah, actually.
They are so faithful, so they never change this time limit. How wonderful they are. Okay, that's
Okay, and here this first line is a comment line, and here you can define the point group, and we put the Cartesian coordinate. Here I use the butadiene for this test presentation. And after making this input file as a optimization.imp, we use NEGMS script for submitting jobs. You just simply NEGMS and your info file, that's all. And then
you don't have to type IMP, do you? I don't know. I don't know how
both works. Both works.
Both works?
Yeah.
Oh yeah. I changed the script so that if there's IMP, I just delete. Yeah. Anyway.
Yes.
Yeah. Okay. Yeah.
So let's have a look at the log file. In the log file first, it prints out the gradient of all the atoms. And in this case, after 40 iteration, it reached to the equilibrium geometry. And the gradient, maximum gradient is less than the threshold in the default setting. So this geometry is obtained. And there is a table for MRSF calculations. This column is the index, and this column is the symmetry, and energy in Hartree, and energy in electron volt, and S square value, and transition dipole for 3 column, and the last column is oscillator strength. So when we think about the excitation energy, MRSF is slightly different because MRSF take this reference state, first calculate reference triplet orbit state and get the response state. So this excitation energy in electron volt is a difference between triplet and singlet state, not a singlet state, but so this
this is very confusing. Okay, so I think this is where everybody gave up because they couldn't understand why there is a negative excitation energy is. So basically, 0 is a reference RHF energy. Respect to that, now your singlet ground is a lower energy than triplet most of the time. That's why it becomes a negative. So just remember that. So the number 1 is a ground state singlet, which is minus 3.209. Then you use that as a reference to calculate the other singlet excitation energy. For example, if you take the difference between
here.
Oh yeah, actually the addition, if you add those two numbers, then that was first excitation energy.
Yeah.
So that would be 6.4 EB.
Sorry, how do you define which state triplet and which singlet?
No. You only ask in this case singlet.
Yeah. As you remember, I asked singlet.
Yeah. Also, can you go back? Yeah. And in this input, S square value gives you the spin states. S square.
I see. But you showed C0 minus triplet 1 minus.
2 is a triplet. 2 is a triplet. 1 is a 0 is a singlet.
No. 0 is reference triplet.
No. S square value.
S square.
So as square all 0 means that this is a singlet. Just to let you know that if you don't do MRSF, if you just do spin flip, the regular one, you got the mixture, you will see mixture in S square value, like number 1. And it's supposed to be either 0 or 2, either singlet or triplet. But sometimes you will see number like 1 as a square value. Then it's a complete mixture of singlet triplet. That's what you see in the regular spin flip method. But our method just eliminate that. So now it's just a singlet.
So we don't calculate triplet at all, yeah?
Here you don't have any triplet. Just
no, it is this in this particular example. But for example, we selected not 3 but 5, 10 roots or 10 states. Among them, could we find any triplets?
Oh, yeah. Okay, but then you need to specify triplet in the input.
No. I thought we specified to singlet. It means we optimize in the first singlet state, not.
You optimize singlet ground state, yes, right? But
here which states we if
root you specify state.
Okay, I see.
It's confusing in the beginning.
No, it's okay.
I see it optimized for singlet, and you refer to them, but you calculate difference with triplet. So I see you optimize first singlet. I see you. Yes, you refer to energy of this as because there is But what this is anyway, they refer somehow to triplet like ground state. Just I don't know. It's kind of confused a little bit. Why minus triplet 1? I see that you. Just maybe it's intelligent. I have no idea. Just don't understand.
Could you repeat what is your question?
Why minus triplet 1? I see you multiply. Maybe it's because your method work in this way. Just
because that we calculate. Oh, so this is you calculate the reference. Okay, first. Okay, that's a DFT. We first need to get the density from the DFT calculation. Then we obtain response states. So it's a 2 different calculation is performed. You first calculate DFT, and once you get the density, you get the response of the density calculation. Okay? So the first you need to do DFT calculation. That's in our case, ROHF.
First means ground state, and you refer to energy of.
No. First means the triplet states, not the singlet. Triplet, ROHF triplet is we calculate first.
No. He means first here.
Is index, right?
Spin 0. Spin 0.
What is 0? They're all spins 0. All singlet here.
That's singlet just. Moreover, that's 0, 1, minus 10, 1, minus 3 dot 100. I see this.
Vladimir.
Difference between ground state and triplet, just from.
Yeah, exactly. Yeah, that's the difference. Yeah. In electron volt, because we typically use electron volt for this.
Electron, it's okay. It's okay. It doesn't matter. Just. I miss only this why.
No. So Vladimir, so first in this it is a ground state. The first excited state it is number 2.
I understand. First ground state why 0. Yes, I see. Just what right hand 3.4. The ground state minus triplet. Just this energy.
Because triplet is reference.
Okay.
But triplet means first excited state.
No.
That excitation electron was 0. You see.
No.
That means for this minus ground state, we have the single ground state minus triplet 1. What I see, just. Okay, let's go for just I don't know.
Okay, so I think you will figure it out. Yeah, let's move on. It's just a subtraction, which from which and which.
Okay, and above this table, MRSF prints out electron configurations. So this one, you can see state 1, this one for ground state singlet, and first excited state and second excited state. So here it prints its energy, symmetry, and SKR value, and there's 4 columns. This DRF is kind of index for specific transition, and this is coefficient of that transition, and this is the orbitals where the electron removed and where the electron is become occupied. So let's in MRSF is confusing, so let's have a look at the example. As we know, MRSF take the ROHF triplet as a reference. So we should remember this is the original one. And for this ground state, the biggest coefficient is this one, 16 index. And this one, in this electron configuration, electron moves from 16 orbital, the 16th orbital to 15th orbital. So it means from this ROHF ROHF configuration, one electron from this LUMO 16 moves from here to 15. So then it creates this ground state configurations.
Excuse me, again. I see. That means you construct ground state from triplet.
Yes.
Exactly.
Okay.
You got it.
Okay.
Exactly.
You're starting from
Yes. You got it. Okay. So there is also very strange things going on here, which I like to point out. He said that he just put the electron from 16 to 15, right? You put you take out electron from 16, then put it to the 15. But you cannot do it because it's alpha.
Yeah.
You need to flip it, beta, right?
Yeah.
Otherwise, you cannot move electron from 16 to 15.
Yeah, we flip.
We flip it. That's why it's a spin flip.
Yeah, right.
We flip.
Okay, if we start from excited singlet, what if 16 luma will flip back and start if not from triplet, from first excited stage. If we flip highest electron, is it possible? Just what will do we have different in this case? It's okay.
What's your question?
You starting from what this picture 16 15, yes, it's okay, it's triplet. But if we flip turn 16 to get excited singlet,
right,
the singlet, not ground, but can it work? Or is it?
Yeah, let's say this S1 state, right? So here it says 15 to 15, right? So 15, this electron, alpha electron flipped in the same orbiter, so it forms beta electron, and this electron remains same, so S1 state is constructed in this way. Can you?
So do you understand? It's just a moving electron from one to there. And as you can see, one of the things that another pointed out, if you go to the state 1, for example, Can you point out the coefficients? Yes.
Yep.
That coefficient the largest, so which means that doubly occupied one is a major contribution.
Mm-hmm.
However, there are others. That is the point.
Yeah.
This with just a single calculation, you have a many linear summation of these different configurations is utilized to describe this particular singlet. So if you just use a DFT, regular ground state DFT, you only have one configuration, which is exactly that doubly occupied one only. But with this theory, you have a lot more configurations can be utilized to describe the singlet. That is why it can contain a lot more electron correlation things are going on. And also another interesting point from the, can you point to Lapran's, for example? Yeah, Lapran's figure.
Yeah.
Yeah. So if you put the electron 15 to 16, for example, then you got the double excited ones.
Yeah,
right?
here I have.
Oh, you have, oh, sorry.
Yeah,
Okay.
yeah.
So
actually, yeah.
But this is a magic to me, because that double excitation usually requires 2 electron excitation, right? 2 times of excitation, but you got this double excitation by single excitation, right? From the triplet Lapran. This is the magic. This is why we have a doubly excited configurations in our expansion. And this becomes, in many cases, it becomes a very important. This doubly excited configuration plays a lot in many excited states. So this is an important point, but
yeah, as Professor mentioned, this ground and S1 is mainly dominated by single configuration, but in case of this
yes,
S2 state.
I understand this coefficient. But first of all, in first step, you calculate conventional DFT. After this, we construct some triplet. Okay, and after this, you use this like basic. You can construct new ground state and several. In this case, you get some double excitation and so on.
Yeah. That's
okay.
right. That's
but
correct.
in this case, you can't calculate triplet system after all. Just only singlet. But after this, in this approximation, you can't calculate triplet.
We can calculate triplet too.
Yeah, we can.
Okay.
We have a triplet.
Okay, we will see.
Don't worry. We have both singlet and triplet. Oh, so
Anna, we cannot hear you.
Yeah.
Yeah.
What I see, what state 2, you have 15 to 15 transition. It means that's just flip.
Yeah,
15.
Exactly. Yeah. Just flip. Yes.
Yeah.
Yeah. Sure. Yes.
And this is the main contribution, 15 to 15. So it will be still the main contribution, a triplet style contribution, yes? Or a triplet configuration will the main contribution. Yes, you see, if you from the reference 15 to 15.
Yeah, but then you flip spins.
You flip spins.
Yeah.
Oh, yeah, flip spins. Yes. Yeah, it's singlet. Yeah. So
it's confusing, I know.
Yeah.
But there is even more confusing would be that this is only M sub S states. In terms of M sub S, M sub S, you just count the number of alpha and number of beta. M sub S 0 means that the same number of alpha and same number of beta. So you create from M sub S plus 1, which is Lapran's, and you create M sub S 0 configurations. Using this M sub S 0 configuration, if you take a proper combination, you got the singlet and triplet both. Because you, in the case of triplet, you also have M sub S 0 triplet, right? So what we generate is an M sub S 0 configuration. From these, by proper combining these, we can get singlet state and triplet state both. So that's okay.
Okay. So after finishing this optimization, you can visualize the molecular orbitals. But you have to be careful because MRSF only prints out RHF triplet orbitals. If you simply just open this your log file with magmal plot or Morden and ChemCraft, you can see the molecular orbitals. In this case, I opened with magmal plot. But you may be interested in the nature orbitals.
Okay, so what he's this is also confusing. Okay, this is also very confusing. The reference is RHF. We optimize first the DFT, RHF DFT. And that means that we optimize ROHF orbitals variationally. So the orbital we are looking at is ROHF reference orbitals, which should be different from S0, the response singlet orbitals, right? So we need to do additional calculations to get it, okay? So if you don't do it, the orbitals you have is reference orbital, ROHF orbitals. So that's what Woojin is going to tell, yeah.
Yeah, and we can see there's a 1-and-1 occupations. It means ROHF triplet orbitals. So to get the natural orbitals, all you have to do is just change.
Natural orbital means that you want to get ground singlet orbitals.
Yeah, that specific state.
But then usually what you have to do is that variationally you need to determine the ground singlet orbitals. But since we don't do it here, so we do it differently. So that's why we call it natural orbital. We don't do the variational, I mean, we don't do SCF. To get the orbital, you have to do SCF. But we don't do it together. So, okay, so also confusing. But so instead, we try to relax those orbitals from RHF orbitals to ground singlet orbitals. That's so that's this is a natural orbital is a way to get it.
So all you have to do is just change the Lund type to gradient calculations, and you have to choose the target state to the state you want to see. If it's ground, it should be 1. If it's first excited state, and it must be 2, and so on. So I gave the optimized structure, and actually this natural orbital calculation is only implemented in this pass. Actually, I checked, and EJMS doesn't have this doesn't
so
print.
I will create one for you. Okay.
Yeah.
Simple. Yeah. Script.
Yeah. So after submitting this, we can, if you open this log file, we can see one more options. We can see these TDDFT natural orbitals, and here you can see the occupations are changed. Because this is ground, this is almost closed shell type, and you can see its natural orbitals. Okay, then we move to the Hessian calculation to check the optimized structure is really true minimum or not.
Can you go back? Yeah. So yeah, this is also another confusing point. Why you do the gradients, right? That's the question. It's not gradient that we want. We want the natural orbitals. So why you need to do the gradients? It's because to get these orbitals, we share the same subroutine of gradients. So Soon is kind of lazy enough that he did not create a new one. So he just to say a gradient and he will generate the natural orbitals, okay? So it's not supposed to be gradient. It's supposed, runtime is supposed to be natural orbital. But we couldn't, Okay, so that's what happened. Go ahead. Yeah.
Okay. And Hessian is exactly the same. Just change the run type as a Hessian and give your target state and your optimized structure. So in here, in games, it prints the normal mode, 3n number of normal modes. And here it says, because we have 1 to 6 is rotational and translations. And here we cannot see the imaginary frequencies. If you have imaginary frequencies, you can see alphabet I before this index of normal mode. But in this calculation, there's no I, alphabet I. So this structure is true minimum. And you can visualize this normal mode with magma plot or that kind of program. And the next step is the conical intersection search. So from the optimization calculation, we remember this S1 state as the bright, a big oscillator strength, which means that it's bright state. So we can guess that the photon will excite butadiene to the S1 state. So I did S1 and ground and S1 and S2 state conical intersection search. Maybe I just guessed these two conical intersections are related to the photophysics of butadiene. So just minor, so just little things to change. Run type to conical, and we need one more group now in this calculation. Ix root parenthesis 1. This parenthesis 1 means after this flag, these values are regarded as a list. So it's not just a single value, but just list. So 3 is S2 state in MRSF. So conical intersection between S2 and S1. So we call it CI2anyone. And N state is, we know, number of states. And I root can be one of these two states. You can choose 3 or 2. And the rest is same. You can give you can give any structures actually, but I usually give Frank-Condon structure at the beginning. So in the log file, after a few iterations, we can see this S1 state and S2 state are nearly degenerate. The energy becomes really close. So we get the we get the conical intersection. So do you have any questions here? Otherwise, I will move to the final NAMD simulation. Okay, then let me continue. The final non-adiabatic molecular dynamics simulations. So on the left side, this is what we have seen until now. You just need to change the run type to the MD. And TDDFT, in TDDFT group, we need to change these two values. N state, we know N state is the number of states to be calculated. But you have to be careful when you do the MD simulation, because if you give really big number, let's say 10, it will calculate up to 10 excited states at every iteration. So it reduce your it wastes your time. So you should set a reasonable number of states. And and iRoot is should be bright state or no. It means which state you want to excite. So it means we will excite butadiene to the S1 state, because from the optimization at the Frank-Condon S1 state as a bright state with the big oscillator strength. So that's why I excite to the S1 state, not the other state. And for this geometry, as Professor mentioned, we sample this geometry, and actually this is velocity of the atoms. We sample these two parameters from Wegener sampling. So these two will be generated by Wegener sampling. And finally, we have one more MD group. In this MD group, okay, you should turn on this read flag, because read means it will read these velocities. Otherwise, games generate random velocity. And these are the ensemble to be used. And the total is the elapsed time. In this case, because this is initial calculation, so this no elapsed time. And dt is the delta, the time step. In this case, I set 0.25 femtosecond. And this is the total number of steps to be continued. And actually, I think this threshold, this option is really important. This is not implemented in original games. Sungun coded this one. This means the threshold of energy gap for restricting surface hopping in K-kappa-mo, which means that if the energy gap when the hopping occurs is greater than the threshold, it will be blocked. I will explain it more details in the next slide. So if you after submit, you can see the log file. Here, first it calculate the overlap, integral, and non-adiabatic coupling for the requested state. Actually, this is not butadiene. I just simply took one of my previous calculation. So this is a bit different, but most of inputs are same, just geometries are different. So depending on this matrix, it calculates the hopping probability from state, target state to the other state. So in this case, the hopping from S1 to S3 has about 0.5% as a probability. And there's a random number at this time step here. So in the surface hopping method, the hopping occurs when the hopping probability is greater than a random number. It compare its hopping probability and the random number, and if this hopping probability is greater than this random number, the hopping occurs. But as we can see, this hopping probability is really, really small, and this hopping occurred due to this really small random number. So because we have limited trajectories, so I don't want this kind of hopping. So this hopping should be blocked. That's why we use the threshold options. So as you can see, this the surface hopping from 2 state to 4 states is blocked by threshold. The energy gap is not fulfilled in this case. So you should test the threshold before submit many NAMD simulation. For example, threshold 5, 10, 15. Actually, it depends on your system, so there's no default value. If you don't give, there's no threshold. So we should...
Basically, it means that the energy gap needs to be sufficiently small to really allow hopping. Sometimes, even though energy gap is large, because of the random number generator, hopping can occur, which is not physical. So we somehow block such cases. So that
like
energy
this.
gap has to be small enough so that we think that this is the case when the hopping really occurs. So kind of artificially we impose kind of restrictions.
Mm-hmm. But if you give too small values, it blocks all the hoppings. But if you give...
Nothing happens.
Yeah. But if you give too big, it allows unreasonable hoppings too. So we need a balance between...
You need to tell us the number, so that's important.
Yeah, but it depends on the system. So actually I use 5 or 10 in most cases.
Yeah, 5 or 10 K-kappa-mole. That's a kind of, that we think that the energy gap has to be smaller than that to really allow any hoppings between different electronic states. So you can see here in this dynamics, the different electronic states is hopping with each other. So even though you start with S2, it could go up to S3 or it goes down to S1. So because of it's dealing with multiple different electronic states, we call it non-adiabatic transition. This is what we call non-adiabatic transition. So non-adiabatic simply means that your electronic states are changing.
Thus, this molecular dynamic simulation, we study the potential energy of we look at the potential energy of the excited states, yes?
No. Just on the fly, it calculates everything.
On the fly. So, what is more meaningful? And we study, I don't understand in which case we should perform the canonical calculations themselves, and when we are interested in molecular dynamic simulations. And
okay, so this is the case when the very early stage of absorption, right after the absorption, then you could have many different things going on there. You excite the molecule as 2 states, but eventually it has to go to the ground states, right? But then initially there might be some sort of electronic transition between S2 to 1 and then S1 to 0. But then we don't know how it is going, how it actually occurs. With this dynamic simulation, we know exactly what would be the possible path of the path of the excited states. So this usually we sub-picosecond dynamics. It's very fast, like a 100 femtosecond dynamics. That's when this kind of thing is happening. But you said that much longer time, for example, millisecond or even longer time, then we more or less in the equilibrium, and that's where there is no such state-to-state transition. Then we just use one single electronic states and do the simulations. But those are completely different dynamics as compared to this. This is, yeah.
I understand, but I don't understand. When we are interested in previous job, the canonical, yeah. Previous input, it was number 4, canonical intersection
Conical
search.
intersection.
Yeah, conical intersection.
Oh, you mean the relation between 4 and 5?
Yeah.
Oh, okay, good. So I misunderstood. Okay, number 4 is a static point. Okay, so there's no time here. We just locate the structure of a conical section. And this might give us some clue how the excited state potential surface would look like, but that doesn't mean that it actually goes that path. So in the real situation, you do have vibrational degrees of freedom, especially really fast motions. That will certainly add additional complexity to this the excited state dynamics. So we do need to include the vibrational degrees of freedom here inside of these simulations so that to see what's really happening. So even though you have a conical section, it will not go to the conical section directly. It may go to the other regions and spend some time, then eventually comes to the conical section, right? There can be many different scenarios. So
okay, but what in this particular example, why we choose 3 to IX route?
Accidentally. Accidentally, you can choose others.
Yeah, you can choose others.
If we just choose different thing and looking what's happening. If we find something interesting, then near this point we start the molecular dynamic. Yes.
Yes. But usually the easier way, finding conical section is difficult. But the running dynamics is easier, although it takes longer. So you run the dynamics and do the initial sampling and see what's going on there. And then you get some idea of the possible structures of conical sections. And you took out those structures and tried to optimize conical sections.
Yeah.
And I see in this conical section job, we have oscillator strength. But when we do not see the oscillator strength and did not see the oscillator strength in previous job
Yeah.
Before.
Here,
not on Hessian, not in the first job. We did not hear here. There is no.
No,
there is. Here. Sorry. I did not look at near the stage.
It's okay. So I like to point out that the size of oscillator strength changes with different structure, right? So initially it has a really strong, large value, but as soon as it can quickly go to the other states, it can quickly becomes a very small number. So then the chance of fluorescence becomes really small, then you would have a much longer lifetime. So these kind of things are quite interesting. And suppose you excite the molecule in the bright states, okay? If the molecule just simply stay most of the time just bright states, then it would emit the light and goes back to the ground. But if it goes to the other dark states right away, then it will not emit the lights and it would just stay there. Then it has a much longer lifetime. So that kind of things that we can see by looking at this, by doing some sort of, So there's a relation between static calculation and dynamic calculation. We probably need both to understand what's really going on. And what's more interesting right now, Woojin just showed a conical section between 2 states, but actually there are 3 states conical section too, which looks weird, but that's also possible, quite ubiquitous. 3 states, well, that's very interesting. You go to that region, then all of a sudden 2 states splitting and the population splits into 2 different states and things like that can be happening, right? So that's also Yeah, we can think about it. Yes.
Okay, here I show the block by threshold, but when the conditions are fulfilled, the hopping can occur. Surface hopping from S2 state to S1 state is occurred. And if you look at the hopping probability is almost 100%. And the energy gap at this point is 0.05 almost EB. So this kind of reasonable hoppings are not blocked, or should be not blocked by threshold. And okay, so with this simple file, we can run our simulation until the end. So, and by sampling and analyzing many trajectories, we can understand the details of photophysics with NAMD simulations. Okay, this is the end. Thank you for your attention. If you have any questions.
So please provide them the info files. Okay.
Yeah, of course.
That's then you can just copy your geometry. That's all you need to do.
It's very fruitful understanding.
Thank you.
But again, about triplet state, just I mean, for example, if I need conical intersection between singlet and triplet,
oh yeah,
can we do it?
That's not a conical section in that case. The different spin states, you can talk to the Michael more about that. That's where spin-off coupling is important. Here, same spin states. Of course, that's a very important different spin state. We want to do it. Right now, we don't have that spin-off coupling. We only have a same spin coupling the calculation. And we really want to have a different spin state so that we can run the dynamics at the same time. So let the system choose whatever it wants to choose. Then we can study both internal convergence, inter-system crossing at the real time. That's a goal.
Okay. But
anyway. No one has done that before yet.
Okay, that means if I TD DFT choose multiplicity 3, could I calculate triplet system instead of singlet?
No.
TD DFT multiplicity take 3. No. I understand just. I understand this point. Yes, that means TD DFT. Now we calculated singlet. Could I calculate triplet system? Separate from singlet, just if I take multiplicity 3.
No, and then you need to say MRSF T.
Yeah.
I see, true, I see.
No, not true.
It's not true.
Just before true, there's T. Okay?
T, it's not true, it's T, okay. It's
MRSF S and MRSF T.
T, okay. But if I take multiplicity equals 3, what's happened?
Oh yeah, then it blows up, I guess. Is that right?
Okay, I see.
Yeah, that doesn't make sense.
Thank you, just.
But what I don't know is whether you can calculate singlet and triplet at the same time or not. I don't know whether someone has done it, because singlet and triplet we calculate independently. Okay, so we can do it, but at least we need to do it at some point, because for the spin-off coupling calculation, we should be able to calculate singlet as well as triplet at the same time, right?
Yes.
I don't know whether we can do it at this moment, okay?
But
or separately, just only triplets.
Oh yeah.
No singlet, just triplet.
Yeah, just triplet or just singlet is possible. That's what I know, but I don't know whether you can do it at the same time.
Okay, I see.
Yeah.
You should move. Thank you.
Yeah. Okay, it's already 2.5 hours. Oh, okay, so